Hey guys, we're back with your final exam review. The last one we did was on limits, and now this lecture is going to be doing 4 practice problems, specifically optimization problems. These are problems similar to ones you can find on your homework 10 and section 4.6. All right. And optimization is a very common type of problem that appears on final exams, which is why I pulled out 4 additional examples for us to go over. So without any further ado, let's get straight into it. The first one we're going to do, wow, right off the bat, I messed it up every time. Looks like a D, number 1. An ostrich farmer has 400 feet of fencing to build a rectangular pen on a field. Very common type of optimization problem. And we want to find the dimensions of the fence plot that maximize the area. Next time I'm going to pause it while I write this. You know, it's always when you get into the video that you realize the things you should do. So, we have 400 feet of fencing at our disposal to build a rectangular pen on a field. We want to find the dimensions of the fence plot that maximize the area. Alrighty. So, when doing something like this, draw a picture. So, we know we want to build some kind of fence. Let's call that Y, let's call that Y, let's call that X, let's call that X. It's a rectangular pen. We have 400 feet available to build this fence, and we want to maximize the area. So we are given that the amount of fencing we have is 400 feet. Another way of phrasing that is the perimeter of this rectangle must be equal to 400. What's the equation for the perimeter of a rectangle? Well, that's just the sum of the sides. So we have 2x plus 2y is equal to 400. We wish to maximize the area. So we need an area formula. But thankfully, we do. Area is equal to width times height. Now we wish to maximize the area. We're going to use the exact same techniques we use when graphing functions for finding extrema. We want to take the derivative, find the critical points, and then do the first derivative test. But the problem is this function a right here, that's in terms of 2 variables, x and y. We cannot have that. We cannot be doing implicit differentiation on these kinds of problems because that's not going to get us where we want to go. So we have to relate x and y together to get a in terms of a single variable. How can we do that? We're going to use the perimeter function. And then using this function, this fixed quantity, we can relate x and y together in terms of each other, sub in here, so the area is in terms of one variable. That might not make a lot of sense, but let's go ahead and try it. We're going to solve for y. So we're going to take this. So that gives us y is equal to 400 minus 2x divided by 2. And that's just equal to 200 minus x. So that's what y is equal to. And then from here, we're going to sub that into here and get a function of one variable. So let's go ahead and do that. So we know the area is equal to xy. But we also know y is equal to 200 minus x. So that gives us the area is equal to x times 200 minus x, which simplifies out to 200x minus x squared. Now that's a function of a single variable that we can work with. So a is equal to 200 minus x squared. Now we wish to differentiate a with respect to x. This is equal to d dx of 200x minus x squared. Why do we want to do that? Because we want to find the maximum. To find a maximum, you have to take the derivative, set it equal to 0, and then solve for x. So that gives us 2x is equal to 200, or x is equal to 100 feet. Take the derivative, set it equal to 0, solve for x. And then that gives us what we claim is the maximum. But the thing is, you cannot just do this and just say, ooh, I found the critical point, it must be a maximum. We have seen a lot of times in the graphing problems that that is not always true. Just because you have a critical point doesn't mean it's a maximum. It might not even be a minimum. It might be nothing. It might just be a little bump in the road. So we have to test it. How, you may ask? Using the first derivative test. So let's go ahead and draw a little plot here. We know x equal to 100 is what we claim is to be our maximum. So we need a couple of test points. I vote x is equal to 1, and then x is equal to 200. Those are going to be our test points. When we plug 1 into the derivative, well, that's very much positive. So the function's increasing on this interval. Now we plug in x is equal to 200 into our derivative. That's going to be very much negative. That's negative. So the first derivative tells us, so the first derivative test tells us that x equal to 100 is where a maximum occurs. Hence, when the top and bottom sides of this rectangular pen are equal to 100, we maximize our area. But we need to find all the dimensions. X is equal to 100 is just one dimension. How can we find the other? We take x equal to 100 and we plug it in right over here into this guy. So that tells us y is equal to 100 feet. Is also another variable that gives us the maximum. So that means our answer is the fence, or the area, is maximized when x, y equal 100 feet. Now, what do we call it when the sides of a rectangle are equal to each other? A square. Fun fact, when you have a rectangle like this, and you're counting all four sides, the square maximizes the area of your shape. So this is the process we do in optimization. We have a function we wish to maximize, and then we are given some kind of fixed quantity that we can use to relate the variables together, so we can solve for the variables, sub them back into the original equation, and then we can use our differentiation techniques and all the theory we developed in the early chapters of chapter 4 to get this job done. All right? Make sense? Excellent. If it doesn't, shoot me an email and I'll help you work that out. All right. So that's it for that example. Let's move on to another one. What I'm going to do is I'm going to go ahead and pause it and I'm going to write out the question and then we will continue. All right. So here's our next problem. An alpaca farmer wants to enclose a rectangular area and then divide it into 3 pens with fencing parallel to one side of the rectangle. There is 930 feet of fencing available to complete this job. What is the largest total area of the 3 pens? All right. So once again, best thing to do, draw it out. So we have a farmer who wants a rectangular pen, one big rectangular area. But then what he wants to do is to divide it into 3 like small pens inside. So what we need to do is add 2 more pieces of fencing down the middle. So now we have, pin 1, pin 2, pin 3, so on and so forth. What we want to do is figure out the maximum area that these 3 pins can have. All right? Now, first thing we need to do, name everything. It's called the vertical one's Y. And and the horizontal one's x's. So this is just like the last problem we just did, except we have these two additional fences on the inside. So given those extra restraints, how does this problem change? That's the whole question. All right? So we are given in the problem that 2x plus 4y is equal to 930 feet, right? We are also given that the area of the pen is equal to x times y. All right? Now here, I think it might be easier it might be easier to solve for y or x. Yeah, let's solve for y here. Or do we want to solve for x? Let's see. If we solve for y, we're going to have to divide by 4, and so we're going to have a half x. That doesn't seem like very fun. So let's solve for x and then do this all in terms of y, shall we? Let's do that. Okay. So from here, we can conclude that x is equal to 930 minus 4y over 2, which is equal to 465 minus 2y. Alrighty? Now that we have x in terms of y, what we can do is go ahead and sub back in to our original area formula, which is what we're going to do now. We wish to get this function, a is equal to x, y, in terms of one variable. Now we have x in terms of y. So that means a is equal to 465 minus 2y times y, which is equal to 465y minus 2y squared. All right, looking good, looking good. All right, now what? Well, we wish to differentiate this area formula with respect to y. Why? Because we want to use the properties of the derivatives to find our maximum. So we take the derivative a with respect to y, that's equal to 465 minus 4y, right? Now we want to set that equal to 0, or 4y is equal to 465, and then that means y is equal to 100 and what did I just say it was? 116.25. So that's what we're going to say y is equal to. All right? So now that we solved for y, we now need to test that this is in fact the maximum. How do we do that? First derivative test, guys. First derivative test. So this is going to be y is equal to 116.25. Now we need two test values from each region. We need a test value from each so we can test the value of the derivative to determine if it's positive or negative on the interval. So let's pull out y is equal to 1 here, and let's pull out y is equal to 200 here. All right? Now from here, we plug in y is equal to 1 into the derivative. Well, that's definitely going to be positive. Now we plug in 200. Well, now let's look at that. What happens when we plug in 200? Well, that's also going to be positive. Sorry, I got distracted there for a second. My dog decided he needed scritches right then and right there. So Bear should be happy for a little bit. I apologize. So for this y is equal to 200 test value, we plug this into the derivative. That's definitely going to be negative. What does that tell us? This point is in fact a maximum. So we have max at y equal to 116.25. Alrighty, but what does it tell us about x? Well, we actually have a relationship between y and x. So what we're going to do is we're going to take this y value and we are going to plug it into here and then solve for x. So that tells us x is equal to 465 minus 2 times 116.25 equal to 465 minus 232.5. Well, that's equal to 232.5. So, what does that tell us? That at x is equal to 232.5 and y is equal to 116.25, we have our maximum. Hence, when x equals 232.5 feet, y is equal to 116.25 feet, we have our maximum. So that's how we solve this problem. The exact same technique. We have the equation that relates to variables. We have the equation we wish to maximize or minimize. Solve for one variable in terms of the other, sub it in, take the derivative, set it equal to 0, find the critical point, test the critical point. If it is our maximum, you're done. And that's all there is to that problem. All right, since that's it for that problem, I'm going to pause the video here and I'm going to go right up the next one and we'll do that one. All right, let's give this problem a swing. A rental car company charges P dollars per day where the price ranges between $60 and $150. It has found that the number of cars rented per day can be modeled by the linear function n of p equal to 750 minus 5p. How much should the company charge each customer to maximize revenue? Okay, so n of p is the number of cars that they rent out per day based on the price, all right? And we wish to maximize our revenue. So your first instinct might be to try and maximize the number of cars rented, but that's not necessarily going to give you the max amount of profit. If you can rent out a whole lot of cars, but if you're doing it for too cheap, you're not making as much money as you could have. So you don't want to rent out necessarily as many cars as you possibly can. We want to find that right balance between the price and the number of cars to get the job done. So that's what we're going to work out. We don't want to maximize the number of cars. We want to maximize the revenue. How do we calculate the revenue? Well, let's just think about this. What is your revenue? It's how much money you take in, right? So how much money are they taking in? Well, they're taking in P dollars per car. But how many cars are they renting? N of P. So we can actually build our own revenue function R of P, which is equal to N of P. So the number of cars based on the price times the price per car. But what is N of P equal to? 750 minus 5P times P. So our revenue can be calculated by 750 minus 5P. That's the number of cars times the price per car. So now we have our revenue function. This is the function that we wish to maximize. So let's get straight to it. So we have R of P is equal to 750 minus 5P times P, but that's also equal to 750P minus 5P squared. So this is the function we wish to maximize. How do we maximize it? Well, we take the derivative, find the critical points, and then we use the first derivative test to test it. But there's one other condition we have to take into account here. It's on the closed interval 60 to 150. So if you remember the extreme value test, not only do we have to test the critical points, we also have to test the endpoints. So what we're going to do is prove that whatever solution we get from this equation is a relative maximum. Take that relative maximum, these two endpoints, check all of them. Whichever one gives us the highest revenue, there's our answer. So to do this, what we need to do is calculate our derivative. So let's take our derivative. So I'm going to take the derivative of R with respect to the variable P. And if you heard that loud noise, that is my dog who has decided to be very energetic right now. Is equal to the derivative with respect to P of 750P minus 5P squared. I'd appreciate if you stop smacking me with that. Is equal to 750 minus 10P. All right? Now, what we need to do is set this equal to 0 and solve for P. So I set it equal to 0. We get 750 is equal to 10P, or P is equal to 75. So that is our critical point. Now we need to use the first derivative test to determine if this is in fact a relative maximum. So let's plot this thing. This is 75. Now we need to pull out our test values. So let's say P is equal to 100, and then P is equal to 60. Let's go ahead and knock out two birds, one stone. What I mean by that is we need to calculate what the revenue, we already need to deal with 60, so might as well go ahead and start playing with that. So if P is equal to 60, then that means this function is the derivative is going to be positive. That means this function is increasing. P is equal to 100, it's going to be negative. So what does that tell us? We have a relative maximum at P is equal to 75. So P equal to 75 is where we have a local max. Now we need to test P is equal to 75, 60, and 150 and plug it into the revenue functions and see what they give us. That'll determine which price gives us the maximum. So R of 60, well, let's figure that out. So by doing those calculations, we can conclude that R60 is equal to $27,000. R75 is equal to 28,125, and R150, not kidding, is equal to 0. Yeah, equal to 0. So we have these three values. We have our critical point and our two endpoints. We tested in the revenue function to see how much revenue you'd make, and it looks like at P is equal to 75, the revenue is $28,000. So the company should charge $75 per day. You can charge $75 per day, you maximize your revenue. Because you think about this, if it's too cheap, you do rent a lot of cars, but you're not making too much money off of it, so your revenues aren't as high. But if you make the price too high, nobody wants to rent your cars. Hence, you have a problem. So the company should charge $75 today to maximize its revenue. All right, now I'm going to pause this problem, and so I can go right down the next one. So a cylinder is inscribed in a right circular cone of height 7 and radius 4. What are the dimensions of such a cylinder which has maximum volume? Okay, so this is probably going to be the hardest problem we're going to do today. So this one, a picture is vital. We absolutely have to have a picture. So let's suppose we have our right cylinder cone. What we want to do is figure out how big of a cylinder we can fit in here such that the volume of the cylinder is maximized. So we know R is equal to 4 and H is equal to 7. Okay? So what we need to do is try and figure out how to set up our equation. We know that the volume of a cylinder is given by pi r squared h, but that's in two variables. So we have to figure out how to relate r and h together. We have to use the fixed information. Now this one we're going to crank out a little geometry called similar triangles. This is something you should have covered in your trigonometry geometry courses. So right here in this picture, we're looking at it from kind of a bird's eye view, but let's look at it flat. So we have our cone, and we know inside we want to fit our right cylinder, right? Sorry, I'm going to make that a little bit cleaner. So we have our right triangle, then we have our cylinder, and then this has height 7 and then radius 4. So we need to use this information to try and figure out the size that we need. We're going to use these two rectangles. So if we want, we can kind of zoom in on this rectangle here. Why'd that turn blue? So we can zoom in here. And let's look at this. We know that this outside triangle right here, we know its dimensions. This pink triangle right here. We know the pink triangle has base 4, height 7. But also, if you notice, if you look carefully, right in here, another triangle is forming, which is this part of the triangle. So this red triangle is similar to the pink one, and that's one we need to solve. Why? So you look here. This distance is the radius of our cylinder, but it's also the base of this other triangle. And then this height right here, what that is it's the height of our cylinder minus 7. So this is 7 minus h right here. The whole thing is 7. This piece right here is the height of our cylinder, that's h, so this is the difference. So this red triangle has dimensions r and 7 minus h, because the height of this rectangle or triangle right here is 7 minus h. Because the whole thing is 7, this piece is h, because that's what we're calling the height of our cylinder, so this difference is 7 minus h. Right? So, what's neat is that these two triangles are similar, i.e. the proportions, so the heights and the widths are the same. In other words, we can conclude that 7 over 4 is equal to 7 minus h over r. The ratios are the same since they are similar triangles. Now, we can use this to relate h and r together. But over here, we have to square the r. So I don't want to do that. So let's solve for h here in terms of r. So from here, we get 7r. That implies 7r over 4 is equal to 7 minus h, or h is equal to 7 minus 7 over 4r. And that's how we can relate the variables together. H is equal to 7 minus 7 over 4r. That comes from the similarity of these triangles, where we build these triangles using the information we know and the information we wish to solve for. So we know h is equal to 7 minus 7/4 r. Sub that into here. And so we get v is equal to pi r squared times 7 minus 7 over 4r, or 7 pi r squared minus 7 pi over 4r cubed. Now this is the volume we wish to maximize, so now we need to take its derivative. So we get dv dr is equal to 14 pi r minus 21 pi r squared over 4. Now we wish to solve for the r that gets this job done. Alright? We just need to set this equal to 0. So notice we have a 4 down here. Don't like that. So I'm going to multiply everything by 4. So this is equivalent to 56 pi r minus 21 pi r squared is equal to 0. We can factor out, let's see, is there any common terms? Actually, I believe so. There is a common term between 56 and 21. Take a second to see if you can figure out the common term between 56 and 21. That's right. It should be 7. So this can factor in 7r times 8 pi. Ooh, you know what? We can pull out the pi as well. So we get 7 pi r times 8 minus 3r squared is equal to 0. With me so far? I pulled out a 7 pi r from both terms. Now, this is equal to 0 if and only if r is equal to 0 or 3r squared equals 8, or r is equal to plus or minus the square root of 8 thirds. Everyone with me so far? I hope so. So, we have a few options, but from these options, we can pull out one of these. Why? Radius of 0. That makes no sense. What does it mean to have zero radius? It's a straight line. Don't really care. Now, what about negative radius? Don't care again. So the only critical point we care about is r is equal to the square root of 8/3. How do we get that? We use similar triangles to relate the two variables together, and then we sub that in to the volume function, and then we take the derivative, set it equal to 0, factor that equation, and now we're just solving for the variables that get the job done. So now we need to use the first derivative test to test this value. So, do our first derivative test. Here is r is equal to the square root of 8/3. Let's plot a test value. Let's say r is equal to 1 and r is equal to 10. We plug these values in. What do we get? Well, we plug in 10. That's going to be positive. That's going to be negative. So this whole thing here is going to be negative. We plug in r is equal to 1, positive, positive. So it's going to be increasing. So that tells us when r is equal to the square root of 8/3, we have our maximum. So when you take this r, sub it back in to here, and you get your h, and then you have the dimensions of the right cylinder that has maximum volume inside this right cone. And that's how you get the job done on that. So that's optimization. Sketch out your situation, figure out what function you want to maximize, figure out how to relate your variables together, get that original function in terms of a single variable, differentiate, set equal to 0, first derivative test to test the value, and then voila, that'll give you your answer. And that's pretty much the standard technique you want to use when you tackle all these optimization problems, all right? Okay. So that's all I have for you on this review of optimization. So if you have any questions about these, please do not hesitate to shoot me an email, and I'm happy to go over anything in more detail with you if you so choose. All right? Okay. I will see you next time where we will have more fun with math.